My name is Nicolae Estrade. I am a graduate student in Luca Mazzucato's lab at the University of Oregon. Our collaborator is Mirav Stern at the Hebrew University of Jerusalem. Today, I want to present some of the work that we do in our lab. In particular, together, we will take a journey in the world of timescales and dynamic neural activity. It shouldn't surprise any of us that the brain forms spatial hierarchies. However, the brain can also be structured into temporal hierarchies. For example, the temporal dynamics or timescale of neural activity in different cortical areas of the brain differ, from short timescales in the sensory cortex to large timescales in the prefrontal cortex. At the same time, experimental evidence shows a heterogeneity of timescales ranging from milliseconds to minutes in the same cortical area. There are multiple studies that highlight the benefits of leveraging computations on multiple timescales when performing tasks in primates, but also artificial neural networks. While the presence of heterogeneous timescales is a well-documented phenomenon, the mechanism generating it is not yet known. And this is where we come in and try to fill in the gap. In this work, we present a novel neural network able to generate multiple timescales in its dynamics. We believe that by cracking the mechanism problem, we can unlock new insights into studying and analyzing neural behavior, in particular regarding learning, adaptation in a volatile environment, and task performance. We followed the work of Abbott, Sompolinsky, Crisanti, Somers, and Stern and consider a rate-random neural network made of functional assemblies, clusters of neurons. The clusters are interconnected and their connection strengths are extracted from a normal distribution of mean 0 and variance g squared over n. The novel aspect of our network is that we consider heterogeneous self-couplings. You can think of the magnitude of the self-couplings as an indicator of the size of the cluster. We can analytically study the network through the use of dynamic mean field theory. We don't have to dive deep into the math, however, the main point to remember from here is that given a large number of clusters, we can simplify a system of n coupled ordinary differential equations to a smaller number of coupled ODEs, that is, the number of distinct self-couplings. The mean field equations have a common term that can be interpreted as noise, whose statistics we can also derive, and that serve as a self-consistent condition. Let's look at the particular case where we have two equal populations of clusters with distinct self-couplings S1 and S2. The mean field analysis allows us to simplify a system of n coupled ODEs to only two coupled ODEs. A further analysis over the values of the self-couplings reveals three types of behavior. We have the classical decay to zero, we have the transient chaos, which reaches a large number of fixed point, and we have total chaotic behavior. These results are consistent with previous studies of rate networks with no self-couplings and rate networks with one self-coupling. We will focus our attention on the chaotic region from which we can extract the timescales of the network, which is quantified as the width of the autocorrelation function at the half height. We observed that the network of multiple self-couplings generates multiple timescales. And the larger the difference between the self-couplings, the larger the difference between the timescales. In the case where the self-couplings are extracted from a log normal distribution, we can see that our network exhibits multiple timescales that vary over a large order of magnitudes. Besides building a network with heterogeneous timescales, here we also introduce a novel analytical analysis of clusters with large self-couplings. In a network, the dynamics of the large self-coupling probe units fluctuates around two critical points and switches between them at random times. This behavior can be viewed through a Fokker-Planck formalism with added colored noise. The colored noise is the contribution from the clusters with small self-couplings. The unified colored noise approximation to the Fokker-Planck formalism allows us to analytically determine the timescale of probe units with large self-couplings. Another aspect that we considered is how the network with two self-couplings reacts to input. Hence, we drove the network with an external broadband stimulus consisting of a superposition of sinusoidal signals with distinct frequencies. We found that the subpopulation with slow intrinsic timescales preferably entrained its activity with slower spectral components of the broadband stimulus, and vice versa. The subpopulation with fast intrinsic timescales preferably entrained its activity with fast spectral components. This effect was quantified via the modulation index of the power spectrum density. Let's summarize the main points of this presentation. One way to generate heterogeneous timescale is by considering a random neural network made of clusters of neurons with heterogeneous self-couplings. The strength of the self-coupling is proportional to the size of the cluster. We have also presented a novel way to analytically determine the timescales of clusters with large self-couplings through the unified colored noise approximation to the Fokker-Planck formalism. And finally, when considering a broadband input, our network with two distinct self-couplings suppressed chaos on a population-specific basis. In particular, the slow populations entrained slower spectral components, meanwhile the fast subpopulations entrained fast spectral components.